Let's prove what's known as Fubini's theorem for infinite series, that the order of summation for a double-indexed sequence A sub mn can be interchanged under the condition that the infinite series of the absolute value of the underlying sequence converges. That is, it doesn't explode off to infinity. A timestamp is on the left if you're already familiar with basic facts about series. Let's get started. If this is the first time you're seeing something like this, a natural thought to have is, isn't this obvious? Can't we always switch the order of summation? Well, this is true on a finite scale. If we lay out every element of a sequence in a grid like so, it is easy to see that we can change the order of summation. However, the introduction of infinity makes this situation a lot harder to deal with. Let's look at this counterexample. Sum it horizontally, then vertically, and you get 1 as a result. Sum it vertically and then horizontally, and you get -1. If you sum it sideways like this, you get 0. In fact, you can get pretty much any integer as an answer. This is why our condition here is so important. In this case, it fails terribly, like so. Let's look at single-indexed sequences in more detail. The condition here is known as absolute convergence. This just tells us that the series behaves as we would expect. It is, of course, convergent. We can change the order of the sequence without changing the sum. Every subseries is convergent. We can split the series into many different subseries and sum them separately, and the overall sum stays the same. Nothing of the sort holds in series that are convergent but not absolutely convergent. Let's take advantage of the properties of absolutely convergent series, namely this one here. First, let's formalize our statement. Let S sub p be disjoint subsets of the natural numbers and the union of all S sub p equal to the natural numbers. Then, we can sum the series as a sum of subseries, as indicated by our sets S sub p. For those confused by this notation, all we are doing is splitting the set of natural numbers into many different subsets, summing each of the subsets, and summing those sums together. This should be equal to our original series. Since our series is absolutely convergent, all of our subseries are convergent. I will show a quick proof on the screen. Let our subseries converge to L sub j each, and the main series converge to L. By definition, the following is true. For those not familiar with this notation, what this means is that we can choose any small epsilon larger than 0, and eventually all the partial sums are at most epsilon distance away from the limit. So we get closer and closer, hence convergence. The following section might be difficult to follow, even for those with some experience, so I will include an example case at the bottom to show what's going on. I'll set epsilon such that m is here, and I'll set n here. Define subset J of the natural numbers as follows. What this means is that we're having J contain all x such that every set x has at least one element less than m. In the bottom example, this corresponds to J containing 1 and 2. Let K be a superset of J, defined in a similar way but using n instead of m. In the bottom example, K would also contain 3. Now, let's find a finite t sub j for every number in K that is a subset of Sj containing every number below n. For example, t sub 1 in the example here contains 1 and 3. Because S sub j is convergent, the following holds. In fact, we can choose another epsilon multiplied by the cardinality of K and use that instead, since it makes future calculations simpler. Now for the final stages of our proof. For given m and epsilon, we should always be able to find j such that the following converges. We want to prove that this converges, so we prove that this is smaller than epsilon. Let's prove this with a series of inequalities. Using the triangle inequality, we have the following. A further triangle inequality moves the absolute values in like so. Let's use what we know and simplify this expression. The sum of every element a sub I for I in S sub j is just equal to L sub j. And we already established that this expression is smaller than epsilon over the cardinality of k, so let's replace it. This double sum just sums all a sub I smaller than n, and we can replace this. Now, we have established that this expression is smaller than epsilon, so we can replace it. Now, this expression sums epsilon over the cardinality of k times, so we can replace this with epsilon. Now, this is the final expression. We can always choose half the chosen epsilon, so we can get rid of the 2. The sums converge to the limit. Now, we can finally prove Fubini's theorem for infinite series. Lay the underlying double index sequence into a grid. Now, arrange them like this. We have just turned a double index sequence into a single indexed one. Here's a note if you want to fully formalize this process. It involves defining a 2D function sigma on the natural numbers and ensuring bijectivity. We can quickly verify that our single indexed sequence is indeed absolutely convergent. Now, take the elements that were originally in the first row and sum it. Take the elements that were originally in the second row and sum it. And so on. Doing this for every row and adding each sum together, we have already proved for absolutely convergent series that this is equal to our new single index sum. Now, do the same for each column, and it will similarly equal to our single index sum. We have reached equality.